All right, folks. So this is going to be sampling solids that we left off on. Now, notice that liquids and solids tend to be quite different in your sampling. Liquids have small gradients as you go up and down and side to side if you don't mix them. If you mix them thoroughly, they typically don't have significant amount of gradients, though if it is a multi-phase sample that you have something that doesn't mix particularly well, you could still have some gradients. However, solids typically end up being heterogeneous. Okay, you can get homogeneous solids. These would be very, very pure alloys. But even those, I wouldn't guarantee you that even if you got like this metal that's in the chair legs here and you tried to sample that it would actually be homogeneous. Okay. Now, heterogeneous solids, these can be monolithic solids. That would be things like steel or concrete. They could be granular solids. They could be things like coal ash, soils, lake sediments, or sand would be a very, very common one that you would see. Grab samples are going to be collected using spatula and spades. That's actually one you're probably the most used to. Everybody knows what a spade is, right? Yeah. Looks a bit like a spatula, but it's so big that you'd use both hands and your foot. Used pretty much the same way. You just use both hands and your feet. All right. Now, cores are going to provide depth profiles. Everybody's probably seen cores because you've probably seen the like geological cores being brought up, especially maybe Alaska or up in the North Pole. Okay. Sample thief is going to be inserted into granulated solids or powders to sample material within a pile or a container. So this is actually going to be basically a core or a sample thief. They kind of work pretty much the same way. So the more heterogeneous the material, the larger the sample that must be collected to get a representative sample. And so if you want to make sure that you contain your representative sample, you're going to need to core down through it. You're also probably going to need to take several of these cores from across your different parts of your sample. Okay. And how this works actually is you turn it. As you turn, it's going to lower down in here. And it's going to fill these compartments with your sample. And then you turn it back and it's going to allow you to pull that out. Okay. Very similar to how a core works. Cores just are much, much larger and require cooling and a bunch of other stuff because they're much larger and they're going to be boring through more difficult to bore through materials. Okay. All right, so let's talk about the statistics of sampling. So the overall variance, which is the square of the standard deviation. This is going to be the sum of the variance of the analytical procedure and the variance of the sampling operation. Notice that you've seen this formula before. Okay. And because this is how additive variance adds, isn't it? So this is actually just an additive variance. Okay. And so our total variance right here is the S squared. That's going to equal the analytical variance, which is the S squared with an A for analytical, plus the sampling variance, which is the standard deviation squared sampling. Okay. And notice again, that would be that square root of the standard deviation 1 squared, standard deviation 2 squared, which is your additive variance. Okay. Now, notice that if one of these is sufficiently smaller than the other, there really isn't a point in bothering with the other one. If one of these is a 1 and the other one's a 0.001, it doesn't actually make sense to bother with it, right? Which is why oftentimes you can go ahead and ignore one of these variances in favor of just concentrating on the other. Okay. So if we consider a random mixture of two kinds of particles, we have N particles, A and B. These are going to be drawn at random, which would be your typical random sampling. Okay. Now, note that I do want to point out here, random is mathematically useful. We can do mathematical models of truly random systems much easier. A lot of systems and sampling, it's actually very difficult to get a random sampling. Okay. Has anybody heard about like the problems with polling and why they're always off? Hmm? No? Okay. So biology, polling, all these things have similar problems, which is that the sampling is rarely random. Okay? So when you're doing like biology, biologists tend to go places where they're interested in things, and they don't go places where like they have to step in the poop. Right? Or they don't go places where they have to wade neck deep in mud. Okay? And so what ends up happening is that biology sampling is rarely random. It's very, very difficult to actually get a randomized sample in biology. Same thing happens with like psychological tests and with polling, is that both of those tend to be concentrated on very specific areas, which is why like every time they do this person's going to win by this amount, it's always wrong in all politics, right? Because they're polling the wrong places, right? They poll people that are depending on what they want to see. Now, the probability of drawing A is going to be equal to the probability P right here equals the numbers of A divided by the number of A plus the number of B. Basically, if you have 50 out of 100, you have about a 50% chance of drawing that thing that's 50, right? Okay. And so if we look at the probability of drawing B, that's just going to be the number of B up here divided by the total right there. Notice that these are just inverses of each other, right? So 1 minus P equals Q, 1 minus Q equals P. Yeah, pretty straightforward probability at this point, right? Yeah, everybody kind of probably... You are. They're doing it. Yeah, you're doing it at an even higher level. Yeah. Yeah. No, everything comes together and reinforces. Now, honestly speaking, I do need to get a packet of the quant material so I can see it sometime.
They make the book.
Yeah, yeah, it's actually.
Like she has all the power.
Uh-huh.
I'm sure she'd send you the order, but
Yeah, I do need to. Holly would be the bet one. I should.
hers are
Yeah,
really pretty.
yeah. I should check out Holly's. Yeah, I've been trying to get your guys' packet that they give you because I could tie this in significantly with quant, but this doesn't require quant, so I don't want to
Yeah.
completely.
Coding stuff, though, not the like this.
Oh, is it?
Like the coding of like just letting figure.
Mm-hmm.
Like in lecture, we learn how to actually do it.
Mm-hmm. Oh, to understand it.
No.
Cool. Yeah, I might get Holly to send me on that because it would be a nice thing to like reference. Because I'm pretty sure everybody will have quant by this point. Yeah, or be in quant on the two. Okay, so this is the expected number of particles of type A are going to be NP. The standard deviation of many drawings will be this right here. So that's your standard deviation of that number of drawings. Okay, and so that's your standard deviation of your sampling operation. And that's how likely you are to get the standard deviation of what you're going to get for that sample with those number of drawings. Okay. Notice that right there is the Q and P. So P is this one right here. Q is this one right here. This is N. That's the number there. And this is the square root right here. Okay. This is the problem we just did, which everybody got correct, which I'm very proud. And this one right here is just going to be straight up the formula that we just talked about, right? And so your expected number was KCl particles. This is going to be N times P. And so you take 10 to the fourth, right, times 0.01. And that's 100 particles. And so you should get 100 particles of those KCLs. Where did the 0.01 come from? %, right? Which is the KCl. Okay, notice that's the amount of KCl over the total, right? Okay. And then it doesn't need to be in percent. It can be in moles. It could be molecules. It could be whatever. It doesn't matter. Okay. as long as you can compare the two numbers, and it would be a number of things. Okay. Now, 10 to the fourth particles are taken. That's where this number right here comes from. And so if we look at the standard deviation, what that's going to be is the number again, 10 to the fourth, times that p, and then q is going to be the other one, right? The 1 minus that. Okay? And so these are always tightly related. If you had more of these, you just repeat this same pattern over and over, just like you did for the standard deviations where you added those. Okay? Okay, so what's the volume and mass of a sample corresponding to 10 to the fourth particles? So let's suppose our particles are 1 millimeter diameter spheres. And so the density for a volume of 1 millimeter diameter spheres for KCl would be this right here, which is 1.984 grams per milliliter. Your average density of your mixture is going to be, this is right here is a sphere, right? So this is the volume of your diameter of your sphere for a 1 millimeter sphere. And so that's the formula for the volume of a sphere, 4 over 3 pi, and then that right there is the radius. So that's diameter, that's radius. And so that would be your microliters. This right here is again the density of potassium nitrate, which is 2.109 grams per milliliter. So your average density for this sample here is going to be, well, we have 1%, that's the KCl, so 1% of that density is that density of KCl, plus 99% of the density is from the potassium nitrate. And so our average density is that right there for our entire substance. The mass of the mixture containing 10 to the fourth particles is going to be 10 to the fourth times the volume right there. We put it in milliliters in this case because our densities are in milliliters. And then we multiply that by our average density. Notice the average density is where the 99 to 1% ratio is implied. Okay? And so that is going to give us 11 grams. So if we use 11 gram test proportions, then your expected sampling standard deviation is going to be 9.9% for chloride, because 11 grams is going to give you, on average, the 10 to the fourth particles. Okay? And so that's actually how you would actually go about testing that. You take your analytical balance, you'd get your sample core, you'd put that on there, and then you'd expect a standard deviation of 9.9% for the chloride. Okay. Now, these are standard test sieves. So particles can actually be sorted by passing them through a series of mesh sieves. Does everybody know what a mesh sieve is, by the way? Do you guys know what mesh is? Sieve. Okay. So a sieve, you guys ever seen like panning for gold sort of stuff? Or has anybody seen where they take like sugar and they pass it through that little net looking thing made out of metal? Okay. Or have you made pasta? Okay. If you make pasta, that's a sieve. It's the little mesh net thing that you put the pasta, and it keeps the pasta particles on top, and things that are smaller fall through. Okay. You can make sieves of a variety of different hole sizes. The hole sizes are being the mesh. Okay. Mesh typically is the width of the wire. In this case, it's actually the width of the hole size. Okay. So this is going to be your sieve number. This is actually the screen opening size right here. Okay, and it's just going to be like a little metal screen like you'd see on a screen of a window. Okay, just smaller so you can have smaller things fall through. Though window meshes would also work as sieve meshes. Now, so a 16 mesh right here has the square openings that are 1.18, and that's where that matches up. Okay, notice that the sieve number, the mesh right here, the larger the mesh, the smaller the opening, because it actually is referring to the wire. Okay. Okay. So your size range is a 16 to 20 mesh. This would be a particle diameter range that would be 0.85 to 1.18. If you have a 80 to 120, you'd have something in the particle range of a 152 micrometer wire that would fall through. Okay? And so what you can do is you can actually use these sieves to separate out different substances depending on their volumes, right? If the volume is greater than these sieve numbers, it's not going to go through. If the volume's less than the sieve numbers, it's going to go through, right? And it'll pass to the bottom. Okay? That's what you're doing when you're using a sieve for pasta. Water is smaller than your pasta noodles, hopefully. Because you're not going to successfully separate them. So how many grams of 90 120 mesh sample are required to reduce the chloride sampling uncertainty to 1%? You I go ahead and give you one more minute so you can think about it. So you have some idea of where your weaknesses and misunderstandings might be. Please. It will. What's going on today? Well, go ahead and move on here. All right, so we're looking for our standard deviation right here. So that's where we're going to start with, right? And so the standard deviation 1% is what we're looking for. And so 1% is going to be our of the NP here is what we're going to actually try to find here. And so our standard deviation here, this is going to give us 0.01 NP here. If we use the 0.01 and 99, that was the 1 to 99% that we did before, what we're going to find is that N equals 9.9 times 10 to the 5th particles. So the particle volume of 1.84 nanoliters and an average density of this value that we calculated in the previous problem. So the mass required for a 1% chloride sample uncertainty is going to be mass equals the number of particles right here, 9.9 times 10 to the 5th particles. That's what we got from here. This is going to be multiplied by the milliliters each particle takes up, which was from the previous problem's answer. Right here. And so we plug that in with the average density. That's the density for that's a weighted average density, by the way, just like your grades are weighted averages. Okay. And so we multiply these three values together and we see that we would need a 3.84 gram sample there. So even with the average particle diameter of 152 micrometers, we have to analyze 3.84 grams to reduce the sampling uncertainty to 1%. There really isn't a point in using some sort of expensive, perhaps labor-intensive methodology here to get a precision of 0.1%, because the overall uncertainty is going to be 1% from just the sampling, right? We can't actually get much better than 1% from sampling, okay? And this is why, for example, you'll often see that like Pace Analytic or any other analytical company or any other analytical program doesn't just run everything on $500,000 to $1 million instruments that have, 0.1% 0.01% uncertainty on everything, right? Because if your sampling error is in the 1%, then running it at 0.01% for the analytical error isn't worth any additional cost. You don't gain anything, right? So, all right. So let's talk about the nickel ore. We have nickel ore. It's that we're going to crush into particles for sorting and analysis. The parts of the ore that are going to be deficient in the nickel are going to be relatively resistant to fracture. Larger particles do not have the same chemical composition as your smaller particles. This is why they're more resistant to fracture, because they have a different composition. You have to grind the entire ore into fine powder to obtain a representative sample. If we start looking at what sort of mesh, what sort of size of particles that we have, if we are fine particles, remember mesh is an opposite number, higher mesh, smaller particles, okay? Then what we would see is this would be actually a fine particle mesh. It's a very, very fine powder. This one right here is less fine, of course, and this up here would be coarse, okay? And so this would be quite a coarse powder. Everybody knows what fine versus coarse means when we're talking about powders? Yeah, it's the size of the particles. Yeah. So fine means very, very fine or small particles. Okay. Like, okay, good example of this is we have several different sands in lab. We have coarse sand, which is that playground sand you see sitting in the organic lab, right? Big bag. It's like normal playground sand you'd see at a beach. Fine sand, on the other hand, is the incredibly small particle sand that feels like super silky. Okay? And so that'd be fine ground sand. All right. Okay. So this right here is actually the nickel content of those. What do you see about the nickel content as you go from fine to coarse? Less nickel content. Yeah. And so as we go to more coarse, we actually end up with less nickel content, don't we? Notice our standard deviations do not actually correct for that. They are significantly different. Okay. So you have to be very careful when you're selecting your samples, right? Going from fine to coarse, you might think that, coarse ones, fine ones, who cares, right? But remember that there's a difference. Why things don't do what they do is because of their chemical composition, right? So if you get things that don't fracture into fine powder, those things are going to have different chemical compositions than the ones that do fracture into finer powder, right? Okay. The ones that, if you were to just have literally a slope and see how things roll down a slope, the things that roll all the way down to the bottom are rolling down because of reasons, right? It could be that they have less static. It could be that they are heavier. It could be that they do less binding with the glass. Okay? All of these things actually do have effects. If you start doing very precise measurements, then these effects can really add up. Okay? So remember that analytical chemistry isn't just about getting every single measurement perfectly done, right? Analytical chemistry is understanding uncertainty and understanding where your uncertainty is and where your cutoffs are. Okay? That's what real analytical chemistry ultimately is. So this is actually sampling of 24 sodium in the human liver. If you homogenize this, the sample is going to be suspension of small particles in water. This is the counts per second per gram here. This is your sample mass over here. And so how much of a random heterogeneous mixture should be analyzed to reduce the sampling variance here? Your Ks is going to be the sampling constant right there. That's going to be the mass of the sample that will produce the relative sampling standard deviation of 1%. And so that would be your Ks right there. Okay. Notice that this right here is your average. Okay. And so your average should, theoretically, as long as your sampling is a valid methodology, stay the same. Okay. What's going to change here, as long as your sampling is a valid methodology, is going to be your standard deviation. Okay. As you get closer and closer to here, your standard deviation is going to come in. All right. Now, the sampling constant, this is actually m r squared equals ks. M is the mass of the sample drawing. R is the relative standard deviation due to that sampling. Okay. And then ks right here is going to be for the 1% right there. Okay. So, if we were to look at this figure right here, what mass in this figure is going to give you a sampling standard deviation of plus or minus 7%? This is a very, very common chart, by the way, to see in like an analytical chemistry lab where they do the same sort of tests a lot. And they need to actually figure out, like, we got a new sample in, how much do we need to draw this sample? Okay. Like, this is a very standard chart, especially if you have a new instrument you just got and it's more accurate and you need to use that accuracy. So you have less uncertainty from that instrument now, and you need to increase your uncertainty. Okay. All right. So what value here would give us that? Does everybody kind of have an idea in their head of a value, or at least how you're going to do this? Okay. Gotta commit to it. Committing to it, you'll never know. Am I ready? Okay. So we need to figure out the sampling constant right here, right? So what is that sampling constant right there? Okay, that Ks value. And that's going to allow us to do the next part of here, which is the plus or minus 7%. So we need to figure out that Ks for plus or minus 7%. And do you remember your formula at all that I'd given you the previous slide? That. So we can figure out our Ks, right? We can figure it out depending on the mass right there. And that one's our R squared, isn't it? That relative standard deviation. So the relative standard deviation is 7. So we're going to take 7 squared. Our mass is going to end up being 36 grams here. Okay. And that's going to give us an M here. Ks, excuse me, is 36 grams. That comes from the table here. And that's going to give us a relative mass of 0.73 grams. Okay, so if we took a 0.7-ish sample, a 0.73 gram sample, what does that mean we should expect? Well, our sampling standard deviation should be around 7%, right? Okay. What would happen if we took a larger sample of that? What happens if we take larger samples? Our standard deviation is going to go down, isn't it? Okay, so we were about there, right? If we went this way, we'd get a smaller standard deviation, wouldn't we? Okay. Let's say our testing analytical technique is only plus or minus 7%. Does it really make sense to go over here? No, not really, right? Yeah. I mean, it would probably make sense to go a little bit further and get like maybe a gram or something, or 1.5 grams maybe. But let's say this substance is $1,000 a gram. Does it make sense to grab 10 grams, 30 grams of this? No. No. If we only need 10% error on certainty, do we need more than 0.73 grams? No, we're probably going to be fine, right? As long as we use a reasonable analytical technique that's below that. So let's talk about choosing your number for the replicate analysis. If we assume the analytical uncertainty, SA, is negligible, which it oftentimes is, by the way, because a lot of instrumentation is just so good now. Okay? And notice that a lot of our analytical sampling techniques, the relative errors in those was actually quite low, wasn't it? Yeah. Most of those errors were things like gross errors, weren't they? Okay. Now, when the sampling contribution to the overall uncertainty can be reduced by analyzing more samples. The more samples you analyze, the more uncertainty you're going to reduce there, right? And so if a single sample is expected to give you 7%, how many 0.7 gram samples must we analyze to give you a 95% confidence that the mean is known to within plus or minus 4%? So this is going to be that same sort of t-test that we've done before, right? Because that's that 95% confidence interval, okay? And so the required number of replicate analyses is U with the uncertainty minus the mean here equals T from the student t-test number, right? Times S, which is your standard deviation here, over square root of N. And so this is actually the number we need to end up solving for. This is the number we actually need to understand. So notice that S right here and U right there have to be expressed as absolute uncertainties or both as relative uncertainties. Either way will work for this. We cannot do one versus the other, okay? Because then you would have percentages versus absolutes, right? This wouldn't work. Now, you can actually rearrange this since we want the number on one side, right? So number on one side equals T right here. Again, that's the student's T. You look it up on table 4.4 from your book. That's that 95% confidence interval that we'd have to look up. And this is going to be times the S squared over U squared. Again, this is going to be our uncertainty here. Okay. All right. Everybody understands where the SS comes from? What number would that be? That's the 7%. Exactly. Do we need the 0.7 gram? Does that have anything to do with this formula? No. As long as we know the S value for that, we're good. Okay. Okay, so how many do we need to do that to get to a 4%? So we go ahead and start plugging our numbers in. Okay, so we have 0.04 down here for the uncertainty that we want. That's going to be squared. The T value, if you look up the student T table for 95% confidence and infinite degrees of freedom, is going to be 1.960. This right here is then going to be our 0.07. That's the 7% squared. We go ahead and do our math. Typically, you go ahead and round up because if we round down, what would happen? Can you do a 0.8 test, by the way? No. Can't do a 0.8 test. And you need to round up or else this number is no longer going to be 4%, is it? It's going to be a higher number because we're seeing how many tests we need to do. Okay. And so this would take 12 tests to get this uncertainty down to 4%. Now, this right here gives us an approximation. See the little approximation arrows right here? Because what number did we use right here for the T value? We used it for infinite degrees of freedom. Do we have infinite degrees of freedom? No. So this is an approximation. This would get you pretty close to 4%, but not exactly, okay? So to get that extra uncertainty, we actually need to plug this in for a new approximation. And so we need to approximate our answer repeatedly. Now, I will note here, you can actually go from either direction in your table, okay? What I usually do when I do these is I actually pick a number close to what I think it'll be, okay? And then I just go until we get exactly our number we're trying to get, okay? Or I decide I'm just okay with doing extra tests. One of the two. Usually when I'm running like Spectra, if I need to calculate this, I start from the lower number of ones I would have to run, and then I just keep approximating until I get the a number of spectra that I'm not bother changing that number when I run it. And so I just get slightly better uncertainty. Yeah. But yeah, you can always use a lower number as well to go here. So we plug in the t-value for 11 in this case. We do this approximation again, and we see that we'd get a 14.9 this time, and that would give us a 15. So what you would do is you'd go back through, you'd plug that number in again, and we see that we get a 14.2, which would be 14 for our next approximation. And so we plug in 14, the number t-value for 14 again, and we see that we get 14.4 again. Okay? And so 14 would get us very, very close to that 4% value. I would do 15 personally if I want to be that value or lower for my uncertainty, because I'm not guaranteed to get less than 4%. But having said that, 4% still gives you a 95% confidence. That is fine. We got it. Congratulations. After 14 measurements, you would have your uncertainty. Okay? Okay. Notice, by the way, that reducing your uncertainty like this takes a lot more effort. So if we had a lot of this example was very, very expensive and we have limited amount of this sample, are you necessarily better off doing 14 tests at 0.7 grams? Or would you be better off maybe doing 1 gram and running it 9 times? Okay. And so that is a consideration you would need to make, right? There is positives to both. The 1 gram is probably going to get you a better uncertainty. Okay. But running it 14 times has strengths. You may have noticed that when I asked you to do less tests oftentimes, it's actually really nerve-wracking, isn't it? And like you mess things up, and it's a freaking disaster. So if you only run 3 tests, right, you mess one up, you can't even calculate uncertainty properly. You're done. And you may not have any more sample. Okay? So typically you don't want to go below 5 tests, by the way, because it's very likely you're going to mess one up. And you would actually, there are benefits to having more tests, smaller number of grams. But you do have to weigh those against each other. If you need to have a 95% confidence, you probably aren't going to be able to get much below 0.7 grams in this case, right? If you get too much lower than that, you're going to need dozens of tests, like 24, 36 numbers of tests, okay? It goes up pretty quick. Now, dissolving samples for analysis. Once a bulk sample is selected, a laboratory sample has to be prepared for analysis. Laboratory samples are usually dissolved for analysis. You don't normally keep them as solids because they fall out, they separate, they do various things that are difficult, and it's easier to get a sample homogeneous by dissolving it. What have I always made you guys do whenever you're making your stock solutions? I made you dissolve them, didn't I? So you'd have a nice homogeneous solution to deal with, right? Yeah. So very important to dissolve the entire sample to ensure all the analyte is dissolved. If mild distillation conditions are insufficient, you may need to do acid digestion, or fusion may need to be used. Organic material may be destroyed by combustion, dry ashing, or oxidation with liquid reagents. That's wet ashing. This leaves inorganic elements in a suitable form for analysis. Oftentimes, organic elements have a tendency to do masking. Okay, and so they can actually be quite problematic. Right. Now, you may notice, we'll talk more about this in like instrumental, is like PACE Analytics. When you did the tour and you saw that, if you haven't done the tour yet, they use like these matrices that can absorb materials and release them one at a time. They somewhat sidestep this issue by simply separating the materials. Okay, grinding. You guys did this one. Remember you did an acid digestion with grinding, right? To get your iron out of your tablets. Hey, guess what? Acid digestion, right? Right there. Right here, grinding with mortar and pestle. Okay. Now, note that mortar and pestles come in a huge variety of mortars and pestles, okay? Because the hardness of your mortar and pestle very much does matter. So, for example, there are steel mortar and pestles. These are actually considered some of the softest mortar and pestles. They're very cheap, and they work very well, okay? But if you do anything harder than steel, it's just going to cut through the steel. And you'll just grind off your steel into whatever you're testing. Okay? And so you always have to have something that's harder than the material you're going to test, but not so weak that it's going to fracture and break when you try to do this. Less expensive mortars tend to be more porous and easily scratched. Do you guys understand why the problem with porous? Yeah, it's going to stick inside. Everybody notice that our mortars and pestles but have coloring to them? Everybody notice that when you used it? Why is that? Yeah, they're not super expensive ones. They're fairly cheap ceramic ones, which is fine for our purposes. But it does mean if you're not very careful and you use certain things, they are porous enough they can absorb materials. Even up to the point of like absorbing spinach chlorophylls. Ceramic mortars can be cleaned by wiping with wet tissues and washing with distilled water. You may, however, have to use HCl acid to help you remove and break down whatever's in there. Yeah, somebody decided to start talking right outside of my room. Okay. Hey, at least I didn't shut the door at the beginning, right? Yeah, we both would have been really in trouble. All right. So if you have difficult residues, by the way, this is how we can fix our ceramic mortars and pestles, is use 4 molarity HCl. Boron carbide is 5 times harder than agate. It's less likely to contaminate with samples. It's very, very expensive in comparison to a steel or forget our ceramic ones. I mean, this is like... Okay, so in graduate school, when I did my geosciences stuff, we used to have boron carbide. We also had like jade ones as well, because the jade ones are actually very hard as well. And these things were like tens of thousands of dollars. Okay, so these things can get extremely expensive. This right here is a ball mill. It's actually a grinding device that uses steel or ceramic balls that rotate inside a drum to crush sample to fine powders. It's actually very common use in industry. You'd see this a lot in industry. A shattered box laboratory mill spins a puck and a ring inside a grinding container. It'll powderize up to 150 grams of material. So you put your material in, the little puck, and then you have this ring on it, and you basically rotate it to pound everything into submission, into a nice fine powder. Now, dissolving inorganic materials with acids. So an array of acids are commonly used for dissolving inorganic materials. Substances that do not dissolve in non-oxidizing acids may dissolve in oxidizing acids. Nitric is very common for this. The hot concentrated sulfuric acid, another very common one, very powerful. Or hot concentrated HClO4. Notice this is actually what we were supposed to use for the superconductor. I had to use HCl instead, just because this is kind of dangerous to keep around labs, especially ones where they're going to sit for long periods of time, like where it happens in our labs. Aqua regia is a very common one, very powerful, only typically used where you absolutely have to. And so it's used a lot to dissolve things like gold and platinum. Everybody understands why gold and platinum is listed there? So jewelry metals, gold, platinum, silver, are all fairly resistant to oxidation. That's what makes them the jewelry coinage metals. Gold and platinum are notorious for being very, very difficult to dissolve. And so aqua regia is one of the ways you can do that. It's actually a mixture of 3-to-1 HCl and NHO3. nitric acid. And you just do it volume by volume. This is concentrated HCl, concentrated nitric acid usually, because you're trying to dissolve these and you need very concentrated solutions to do it. But you can make aqua regia at different concentrations. But typically it's concentrated because you need it to dissolve silver and platinum. Strong oxidants like chlorine, Cl2, or HClO4 and HCl can dissolve very difficult materials, and that's why we used them for the superconductor. Now, note here that dissolving with acids can be very dangerous. That's why I had you do that under the hood when you did it. And I was like, you guys need to be very careful, do it under the hood. This is why we did that. Okay. It's important to understand all the hazards before attempting to follow and all safety protocols. You very, very much can dissolve off parts of your body here and cause yourself a lot of problems. It's also incredibly dangerous for your eyes. So, all right. This is some different dissolving acids, by the way. HF is kind of an interesting one because it's a non-oxidizing acid, and it's used heavily for things like silicates. It does a whole series of compounds that would not normally dissolve in almost any other acid. Okay. All right. Again, this one is why we did not use this, because if you get evaporated too much, it is explosive. Okay. And one of the ways that these things can evaporate is just sitting in a lab and slowly evaporating over time, right? Okay. So, microwave digestion. This is an efficient and greener approach. It's used to perform digestion in sealed fluoropolymer, usually is the one I've seen, but you can also use glass or quartz vessels. These are called a bomb, by the way, and they're going to be heated in a microwave oven. Anybody know why they're called a bomb? Out of curiosity, anybody in physical chemistry, have you guys used the bomb calorimeters? No? Oh, that's a shame. Okay. Well, that's sad, unfortunate. The reason they're called bombs is how bombs work is they have an explosive inside of a shell that builds up pressure. And so you put an explosive inside of a shell, build up pressure. You may notice, like, if you build up pressure on your finger and then release it suddenly, bam, right? It explodes out. So that's how they make, like, the bombs they used in World War II, and most bombs are made that way. Okay? So pressurized, and then it fails suddenly and releases all that pressure. Okay? Okay. And so, like, a bomb calorimeter is literally essentially a bombshell. It keeps all the heat and pressure in and doesn't allow it to release. You don't normally allow them to fail. Otherwise, you would regret that, because that would be an actual bomb. Reason they're called bomb calorimeters and bombs in this case right here as well is because originally, back after World War II, we had all these bomb shells. And so we took all these bombshells that had been made and we just like, hey, we can use these for labs. And so you literally would have bombshells from World War II, if you go back far enough, being used for this stuff. They worked really well, actually. And very cheap. It's actually kind of a shame. We need the wars to stop long enough that the manufacturers need to sell these things for cheap. And then you guys can restart wars or whatever. Okay. So what's going to happen is the microwave radiation will directly heat the acid in solution. It's a lot more energy efficient than your typical, like, putting heat, pumping out of the top of like a hot plate. The use of the sealed vessel enables the higher digestion temperature, so you can get temperatures way higher than you normally would. To prevent explosions, your CAS actually releases gases from the vessel if the internal pressure exceeds 55 bar. Note 55 bar is pretty high. Okay? And so it does actually not act as a bomb and blow up, though it does vent. The vessel is going to be cooled prior to opening to prevent loss of volatile products. What would happen if you open this prior to cooling, by the way? Anybody use a pressure cooker? What happens if you open the pressure cooker prior to cooling? It explodes. Yeah. Okay. And so never open one of these prior to cooling. Not only can you lose product, but it's going to violently spray acid in your face and whatever you happen to dissolve in it. So these are some of the greener aspects, by the way. It does minimize sample, chemical, and material amounts, which is always excellent. I try to do that as much as I can. Maximize sample throughput because nothing can escape easily because it's sealed the entire time, ideally. It minimizes energy consumption as well, which is always helpful, of course. So that's your green sample preparation right there. You may notice they're the same sort of things I started your semester off with in the lab, right? Now, this right here is fusion. Substances that will not dissolve in acid can be usually be dissolved in hot, molten, inorganic flux. And so finely powdered unknowns are going to be mixed with flux. Fusion, melting, is going to be carried out in a platinum gold alloy crucible between 300 degrees Celsius and 1,200 degrees Celsius. Now, one of the problems with fusion and flux is going to be the impurities are going to be introduced by large amounts of solid reagent that you add to do this flux, to actually produce that inorganic flux. And so you're adding all these impurities to your sample. But, I mean, it's better than not being able to sample, right? So these are typical fluxes for different sample dilutions. This would be your fluxes right here. And this would be your crucible that you'd want to use. And these right here are your different uses you would actually use it for. Okay? And so notice again, these things are pretty wild if you start thinking about them. They're typically salts of different types that you're going to melt, and that's why the high temperatures. And then they're going to make essentially, these are essentially like lava. You're making fluxes, which is pretty much what lava is. When it's actually molten lava down in the earth. So, in case you're wondering, yeah, it's very similar, or a molten salt reactor would be very similar to this. Okay. Now, so digestion of organic material, this can be usually be classified as these two major things, which is dry ashing and wet ashing. So, dry ashing is going to be oxidation of the organic matter with O2 at high temperature to leave behind inorganic components for analysis. Digestion does not include liquid here. And so does anybody recognize this? We actually burned away filter paper to get rid of it, didn't we? Yeah. So we did dry ashless ashing. Now, this sample is oftentimes heated in porcelain, which is what we usually use, or a platinum crucible. We do obviously not use that. That's very expensive. That would be like your entire budget for all your lab fees for a year. Let's not do that, huh? You won't be able to do anything else. Now, another type of dry ashing is actually microwave-induced combustion. So examples of these are going to be analysis of halogens in coal and metals in plant matter. Very typical for those. Wet ashing is going to be destruction of the organic matter in a sample by a liquid reagent prior to analysis in an inorganic component. So conventional wet ashing can include microwave digestion with an acid. This is a very common way to do this because it typically wet ashes most of your organic materials anyways. One of the important wet ashing processes is actually the Kajadal digestion, and this is for the H2SO4 for the nitrogen analysis. So that was that previous method we had talked about way a while ago now, all right? But that was that one. This right here is a high pressure asher. So high pressure ashers are going to use resistive heating elements inside the chamber here. And so you'll have digestive temperatures that reach 270 degrees Celsius, typically under a pressure of about 140 bar. So it's basically a pressure cooker. The high pressure actually allows the acid to be heated to high temperatures without actually boiling it. And so you can keep the acid in its liquid form at those high temperatures. The high temperature nitric acid oxidizes organic matter without assistance from H2SO4 in this case. Or hydrogen peroxide is going to reduce the nitrogen oxides generated by the digestion of those organic matter. And so this is what this looks like overall. This is going to be a fused silica vessel right here, loose Teflon lid to allow venting. And this is our digestion sample right here. And so what you have is your thermocouple, so you can actually control the heat. This is the heater right here. This is a water bath with 5% peroxide. So let the peroxide out here so it can react. This is going to be a steel autoclave. That's basically a pressure cooker. And this is a fluoropolymer vessel, things like Teflon, that sort of thing. Again, we have a Teflon liner right here and a titanium rack. And so what's going to happen here is you're going to have your acid in here, digesting away. And then you have your peroxide reacting with it. If it goes over too much, over 140 bar, this pressure relief valve is going to allow that to relieve the pressure. Do note that hopefully you don't have to relieve the pressure, or you have good venting systems. Okay. Now, very widely applicable. Hazardous, though. You may have noticed we're using hydrogen peroxide and things like sulfuric acid, right? It is quite hazardous. It is under high pressure, high temperatures. Perchloric acid actually has caused numerous explosions in these. So if you use perchloric acid here, you can boil all of this off at this very high temperature, high pressure that you're doing this at. And then if that gets too dry, it explodes. And so you can have these blow up if you use perchloric acid. First, you're going to want to heat the sample slowly to boiling with nitric without the perchloric acid. Boil to near dryness to destroy easily oxidized material, because nitric doesn't blow up when you have it dry, when you boil it to dryness. Then you add fresh nitric acid, and you repeat that several times so you can make sure you actually reacted away everything. And then you're going to cool your sample. Then you would add perchloric acid, and you'd heat up again. And so nitric acid would be present during the perchloric acid treatment. You always oxidize first with nitric, and you only perform the designated perchloric under the hood, and you always use blast shields just in case you actually boil it to dryness. Because if you mess this up, it's going to blow up and send shards of metal and pieces of the the steel right here flying at you. Mm-hmm.
So it's like you're boiling it to like almost dry.
You boil it to dryness with the nitric.
Okay.
Yeah.
To dryness.
Yeah, it's fine. The only one you don't want to boil to dryness is the perchloric. Yeah. Okay. So you always oxidize first with nitric so you can get as much done without using the perchloric as possible. Yeah. And then you use perchloric to finish it up with a blast shield and hood. Okay. And you do not store perchloric on wooden shelves because if you get any spill, it can dry out and then you'd have explosive cellulose perchloric esters. Yeah, which is basically like gunpowder. Gun cotton is what it used to be called. Yeah, you can make different explosives with it. It's one of the methods you can make explosives, like a gunpowder sort of residue. It just much easier to set off than gunpowder. So solvent extractions. This is one that you got more in organic chemistry, or you will get in organic chemistry more. Very common technique for organic chemistry. So this is a physical transfer of a solute from one phase to another. It's going to be used to isolate desired analytes, concentrate the desired analyte, and it's commonly going to be an aqueous solution that's extracted from an organic layer. Lower density solvents like toluene, heptane. Do you guys have any questions about this material? Let me actually take questions for the last 10 minutes, because I'm not going to be able to just go through all of this, telling you guys each thing. But to be frank, there's not many parts of this you actually need me to explain. They're pretty clear definitions. So, is there any part of this chapter that doesn't make sense to anyone in this room?
Is that it more?
The majority of this is just pure memorization sort of stuff. If there's a formula in here that doesn't make sense to you, please let me know. And try out your homeworks. Next time we're going to start on the next chapter, and I'll take questions. Okay? Also start us with a question. No. I would say that it's probably going to be something like a 60% like definitions, concepts, what would you use for this, what do you need to do with this, and then there'd be some formulas in there. How much you actually need the formulas for those is another question, but like there might be some math, but some of these things you can do just with logic, right? Does that make sense? All right. Let's see. Is there anything that I think you guys are going to have difficulties with here? Do you guys understand pre-concentrations? So in most cases nowadays, you actually have to dilute your solutions. But sometimes if you get a solution, it's too low of concentration, you can't actually detect what you're supposed to detect from that solution. Okay, and so what you do here is you actually concentrate the trace components of a mixture prior to their analysis. You do this oftentimes by doing things like boiling off some of the liquid. And so the easiest way to think of this is actually if you think of like organic chemistry. So when I taught organic chemistry, I do this lab where we like test for caffeine. And what I always end up having to do is I take my coffee and then I boil off about 4/5 of the volume. And I pre-concentrate my coffee to a very, very concentrated solution. And that way you get more caffeine with less of the volume, right? So when you go to do like an extraction, you get a larger amount of caffeine without having to try to do an extraction on 100 milliliters.
So it's kind of like a reverse dilution.
Mm-hmm. Yep, it's a reverse dilution, concentrating. Yeah. You guys are actually doing it quite often at PACE. You're doing a concentration by having, you have these little matrices that bind those substances. And so you're concentrating into that vessel so then you can release your concentrated burst from your sample when you're trying to test it. So you can use things like filters to concentrate. You can use things like binding matrices, of course, to concentrate. You can use things like boiling off solvent to concentrate. You can use things like centrifuging to concentrate. If you do like a biology labs, you oftentimes will concentrate by centrifuge. Okay. Anybody have any questions? Everybody knows diffusion. Okay, so diffusion is random motion of the molecules, and it'll diffuse from areas of high concentration to low concentration just due to probability. Okay. It does have a driving force, though. Convection is the process where the solute is carried from one place to another in bulk motion. That would be things like stirring, flow, like a convection current on your oven. Okay. This is actually the diffusion measurement, by the way. That's diffusion coefficient. And so there actually is a formula to model diffusion and how fast something would diffuse. Okay. This is actually why you typically mix things, by the way. And so this right here would be like well mixed diffusion only versus a well mixed here. So if you have like two samples and you're trying to extract something, you could do it if given enough time with diffusion, but it would take a tremendous amount of time, right? And so what you typically do is you mix it very well and it'll diffuse faster. Okay? If you want a slow diffusion, you would not mix it, right? Because the boundary layer then would be the maximum amount of diffusion you can get. Okay. You can use chelating agents, of course, to do extractions. So like if you had taken the chelating agent, which we used EDTA, we could have extracted the magnesium or calcium, and we would put those then into a new solution, and then you could add something that binds better than the chelating agent, and you can release that metal back out and test it. Keep in mind though, you will likely not get the full amount of metal back out, okay, unless you have a tremendous difference in the chelating agents, that there have very large difference in the formation complex binding. Okay. Okay. So why did we keep raising the pH and we used that buffer last time in the last lab where we were doing it at pH 10 for our EDTA? Why didn't we do that at pH 6? Or for that matter, the next lab? Thank you. Because EDTA at pH 10 is only 0.3 of it in the form that would actually do the binding, right? And so if we lower that pH too much, we get very little of the EDTA in the form that would actually do the binding, and we are no longer on an optimum pH, right? And so this makes it so that we would actually have very little effective EDTA in solution. Okay. Same thing happens with any binding. And so we can lower our amount of effective binding. We can also lower the amount of our chelating agent that can bind to these substances. Notice we're actually going to use that next week. Most of you, I don't think any of you got that done with the sodium hydroxide, right? Where we increase the pH, and that's going to mask one of our substances, right? By causing it to precipitate. Okay. Okay. This right here is different solvents and what we would select them in terms of waste disposal, environmental health, and safety issues. This has been getting kind of weird lately, by the way. There's some of these solvents that are not normally considered super problematic or toxic that's becoming like real targets for people making laws for some reason. But anyways, ethyl acetate here is considered a pretty green one, acetone. Acetic acid is sort of on that dividing point. You'll notice that any chlorinated solvents are anything that is brominated, chlorinated is usually considered very problematic. Little fun side note here. The way that they decontaminate our water and remove viruses and bacteria from our water is with chlorinating agents. And so they actually produce chlorinated and brominated organics in our drinking water. So the government definitely is a do as I say, do not do as I do organization, if you're ever wondering. By the way, the local water, the tap water, is fairly high in chlorinated and brominated substances. Yeah. Because they use that methodology. Which I was pretty shocked about the brominated. That's not normally used anymore. Because they're more likely to come apart and actually react with you than the chlorinated ones. So, anyways. Now you're worried about your drinking water. Okay. Please do let me know if there's anything you don't understand from this chapter. I will go back through and hit those points, okay? Try out the homework. That's going to be a good determinant if you understand the material. Okay? Okay. This right here is a nice little summary chart. If you ever need to go back and design an experimental technique, this can kind of help you structure your thoughts. Okay? Okay. Micro extractions are becoming really important, by the way, because you can work with much smaller quantities, but they are a lot more finicky.